No matter what camera or astronomy equipment we own, at some time we are all tempted to image the planets, especially Jupiter and Saturn. It's why you are watching this video. Each time I have tried it, I learned something about my equipment, mostly through trial and error. And when working with optical systems at high focal lengths, like that required for planetary imaging, there are unique challenges. In this video, I want to walk you through my process step by step. It took me many attempts to settle on this workflow, which I think is highly efficient. I don't consider myself a planetary imager. Over the last 4 years, my telescope and equipment were chosen for visual astronomy and the purpose of imaging nebulae and other deep sky objects with long-term exposure methods. Most of my optical tube assemblies are refractor telescopes with focal lengths and apertures much too low for good planetary imaging. Nevertheless, of course, I wanted to try. Hence, I purchased some accessory lenses, more specifically focal extender lenses, to boost magnifications by 2x, 3x, and even higher. I think many of you are in a similar position. I suspect you too own a Barlow Lens or focal extender lens. To confess, I do also have a Maxitoff 105mm aperture telescope, which I used in a few previous videos for planetary imaging. In many ways, reflector-designed systems like Schmidt-Cassegrain or Maxitoff or Newtonian telescopes are better suited for planetary imaging. But here, let's just focus on the refractor and Barlow Lens combination. So, to begin with, this is my equipment. The telescope is the Zvibony SV503 80ED telescope, which has a native focal length of 560 millimeters. This refractor sits on a AM5 mount from ZWO, and in this video, I will do my imaging in EQ mode. Of course, the rig is controlled by the ASIAIR, actually the Mini, and we'll talk about the rest of the accessories later. The focal extender lens I employ is the Explore Scientific brand. It is very similar to a Barlow lens, but there are some subtle differences in optical design and capabilities that are explained very clearly on the catalog web pages of Agena Astro. I encourage you to read about it. I will use the 3x version in this video, and you may find that I use the word Barlow synonymous with focal extender, even though technically they are not the same. Pardon me for taking this convenient liberty. If you have used one before, you probably know that finding focus with a Barlow lens on a random area of the sky is not exactly easy. The magnification is so high, the field of view is so small, the visible stars are few, especially if you live in a city. So I highly recommend you test your OTA setup at least the first time during the day to get familiar with the focus settings. To begin with, as with any astrophotography technique, for best results, the focused image should be projected directly on the camera sensor on a straight line path out the rear of the telescope. For planetary imaging, it is not necessary to use any reducer or flattener lens. In general, they are not compatible with focal extenders or Barlow lenses. If your telescope is similar to mine, then you might find that it may be impossible to reach visual focus by simply inserting an eyepiece into the 1.25-inch nosepiece assembly at the rear of the scope, if you are using a straight-line configuration. The top image has the draw tube fully extended, and it still cannot reach focus with this eyepiece. So additional spacers are required to actually reach the focus point. And even if they are not required, it might still be a good idea to use them so as not to stretch out the focus tube to its absolute limits, for fear that it might impart some instability on the optical path. The bottom image is at focus and not fully extended because I added spacers. You can see here that I removed the 1 1/4-inch nosepiece accessory adapter and inserted a 2-inch nosepiece accessory adapter with M48 extension rings. These rings gave an additional 35 millimeters of spacing. And then, When I screw the original 1¼ inch nosepiece adapter on that, an additional 25mm more of spacing was contributed. That total equals 60mm added distance to the OTA light path. Now, if you insert an eyepiece directly into this extended tube, focus can be achieved at about 70mm extension of the draw tube, according to its engraved markings. Using this approach, from here you can simply then add the Barlow lens and check it again with the eyepiece or with a planetary camera. Visually, I chose a distant electrical tower as my target for this focus calibration. As you can see here, the tower is about 400 meters away, down the length of my street and behind the distant apartment complex. Using this configuration with the 3x Barlow lens and the ASI 585 MC color planetary camera, focus was achieved almost exactly at the same point that I observed visually with the eyepiece, or at about 70mm of focus tube extension. Somewhat to my surprise, it seems that a Barlow lens does not change the focal point of the light path very much at all. If you are interested, this is the camera and the configuration and specifications for it. And here are some video image views of the tower at 560mm times 3x, or a focal length of 1680mm. The clarity and magnification are quite remarkable, don't you think? I happen to have all 3 of these focal extenders from Explore Scientific, and I tested all of them for the proper focus point on this telescope. Now I don't ever have to determine this again. I know the approximate focal distance for each of these lenses. I also noted that placing the 585 MC directly on this modified OTA, interestingly, required a draw tube setting of about 56mm to reach focus. Also, notice on this OTA setup, I have included a small finder scope. This is a 6x prism diagonal finder scope with a built-in eyepiece and crosshairs. They are inexpensive and many companies sell them. For planetary imaging, having one is critical. I will discuss this in more detail later, but you might want to roughly align your finder scope during the daytime to get it reasonably close. Later at night, we will have to fine-tune it, so don't waste too much time on it now. Here is a photo of my OTA setup a little later when I transferred the scope to the AM5 mount in my backyard. In this workflow, you need to start with the camera first, no Barlow lens. Earlier I determined that the focus point was about 56mm on the draw tube when using this OTA with the M48 spacers. And here I am verifying and precision focusing the camera using a Batinoff mask so I could do an all-sky polar alignment. That is why I removed the Barlow lens at this early phase of the workflow process. If you try to do a polar alignment with a Barlow lens at high focal length, you may find it does not work. It fails presumably because it cannot plate solve with so few stars. At least that has been my experience every time I tried to do it with my 3x Barlow lens. It failed because plate solving fails. However, at the native focal length of my scope at 560mm, the polar alignment and plate solving works fine. Polar alignment precision is crucially important for planetary imaging. Later, when we collect video data, the sensor crop factor for video capture at the most zoomed setting is necessary to get the highest frame rates. So the planet will appear very large in a small field of view, and if your polar alignment is not precise, it could drift away before you finish your video capture. So I triple-checked my polar alignment as you see here on this slide. After triple-checking, I was quite sure that my alignment was at less than 1 arc-minute accuracy. On the night that I captured this data, Jupiter was high in the sky in the evening and quite close to the bright star Aldebaran, as you can see in this 35mm Canon R8 camera video sequence. So it was Aldebaran that I would consistently use to focus my OTA, with and without the Barlow lens, and even in between filter changes, which is something that I also experimented with on this night. So when my scope was focused and polar alignment was completed, I slewed to Aldebaran. Notice during this discussion, we never talked about guiding. You don't need that. If the polar alignment is good and everything is operating properly, with a stable tripod and good quality tracking mount, guiding is not necessary. So here is Aldebaran, a 3-second exposure, without a Barlow lens at 560mm focal length. Adding the bullseye function provided by the ASIAIR, I proceeded to center the star as best as possible in the field of view. I then went to the Mount menu and synced the mount on the position of Aldebaran. The next critical action is the alignment of your finder scope. So with the telescope still centered on Aldebaran, I aligned the crosshairs exactly on the star. To help and assist me with this precision alignment, I used this funky little XY movement control device from Vixen that I previously bought on Amazon.co.jp. I jury-rigged the finder scope with a small set of ring clamps and the Vixen alignment device together for this purpose. Being able to just turn 2 knobs to move the finder right, left, and up, down makes the alignment process incredibly simple compared to adjusting the screws on the ring clamps holding the finder scope. This is my homemade setup. You can probably buy or find something similar in function. With this configuration, it was possible to make Aldebaran completely disappear behind the crosshairs in the finder scope eyepiece. This level of precision when using a 6x or 8x finder is absolutely necessary. I cannot overstress this fact. Once that is done, and we have verified that the finder scope crosshairs and the preview photo from the camera are both precisely aligned, we can then proceed. The next step is to turn off the camera and carefully remove it. Then, gently insert the Barlow lens and reattach the camera to that. Next, pull out the draw tube to the proper focus point that we determined earlier that day. For me, it was around 70mm, if you recall. If you are lucky and you did not jar anything in the process, and you have a good mount like the AM5 that I am using on this night, well, then the star should appear within your Barlow enhanced camera image field of view. It probably won't be exactly centered, but it should be there. This is where it appeared for me after inclusion of the Barlow lens, slightly off-center. So then I centered it, and the next step was to do a precision focus on the star. Eventually, using a batten-off mask, I achieved this final focus pattern. So by using the batten-off mask, I went from the red box to the precisely focused star you see in the center of the field of view on the ASIAIR screen capture image shown here. And for fun, this is a 30-second exposure showing some of the dimmer stars that are located nearby in the same sky region to this massive red giant Aldebaran. So with this setup now at focus, the OTA stretches 79 centimeters from tip to tip, or I estimate about 65 centimeters from the telescope front glass to the sensor. The focal length, of course, is now 1,680 millimeters. Next, I checked once again if the finder scope was still in alignment. I made a few tiny adjustments. After that, I used the ASIAIR to slew to Jupiter, which, if you recall, was quite nearby. Now, since we added the Barlow lens, technically you need to change the focal length setting on the camera menu in the ASIAIR for the slewing to work properly. However, even if you do that, it probably won't work anyways. Again, the focal length is too high, the number of stars too few, and the software is simply unable to plate solve under these conditions. But that is why we have the precisely aligned finder scope. You will probably see that after the initial slew to Jupiter, if you take a photograph, it will not be in the field of view. As you probably know, the ASIAIR is not 100% accurate on the first mechanical movement of the mount. It usually takes 2 or 3 photos and adjustments to get the target centered properly. But we cannot count on that with planetary imaging using the 3x Barlow lens, or so that has been my experience so far. So after the initial slew to Jupiter, you will need to cancel the request to stop the ASIAIR from an endless cycle of plate solving. Then you can look into the finder scope and you should see Jupiter, but skewed slightly off to one side. With the hand controller, under the fine movement control setting, you can then reposition the mount until Jupiter is directly under the crosshairs of the finder scope. Alternatively, you can set the slew rate on the ASIAIR from max to 1x and gently slew using the arrows on your smart device. But for this purpose, I prefer using the hand controller because you need to keep your vision fixed in the finder scope at all times to center Jupiter precisely. After doing this, I take a short exposure image to see if Jupiter is now in the camera field of view. If it is, I can then center it better in the preview mode by taking sub-second images and making adjustments and repeating that cycle until Jupiter is very close to the central crosshairs. For this, because you are now visualizing everything on the SmartPad device, using the screen arrow controls turns out to be easier. Here you can see with a 0.5 second exposure, Jupiter and its 4 brightest moons are nicely visible and in focus in the center of the field of view. At this point, we can shift to video mode. But if you immediately don't see anything, don't panic. Be sure you are on the widest field of view at 1080p and go to your video settings to increase the gain and/or exposure time. When the planet image becomes visible, you can then shift to a more narrow field of view by dropping down to 480p or 240p to digitally zoom in on the image. Here you can see that I am using the hand controller on the AM5 mount, trying to position the planet in the center of the field of view. Although this is possible, it is a bit cumbersome since the controller movements are less refined, a little jerky. So while viewing the planet in video mode, if you get rid of the video settings menu by touching the chevron button, the AM5 movement control menu can be seen on your SmartPad screen. You can then use these arrows to reposition the target more easily into the center of the field of view. Once centered, if your polar alignment was good, the planet should remain within the boundaries of the field of view for several minutes without drifting away. For Jupiter, 60 or 90 seconds is about enough time for a single good video capture. At this point, all that is left to do now is select the proper gain and exposure time settings and record a video in the AVI format mode. Okay, before closing, perhaps we should review or summarize this rather detailed workflow. Number 1. Modify your refractor OTA properly with extension rings to allow for it to reach focus with your chosen Barlow lens in a straight line configuration. 2. Because of the modifications, you should next test the telescope for the proper focus draw tube setting required to achieve focus. This should be done for both your Barlow lens and camera combination, and also for using the camera only with no Barlow lens. It is way more easy to explore these settings during the daytime than attempting to find focus at night. Trust me on this. Remember, the focus point will be different than what you may be familiar with previously, since you inserted several extension rings and lengthened the OTA. 3. Assemble the OTA with the camera, specifically without the Barlow lens, on your sidereal tracking mount. I prefer to do this in equatorial mode, however, Alt-Az tracking will also work for planetary imaging. 4. Once dark, focus your telescope starting with the predetermined draw tube setting that you identified previously. Then execute a precision polar alignment and triple check it for accuracy. 5. Slew to a bright star nearby the target planet. 6. Precisely center the bright star and sync it to the mount. 7. Align the finder scope on the star with the best possible precision. Be very precise here. 8. Turn off the camera and carefully insert the Barlow lens into the OTA configuration. 9. Center again and fine focus the telescope using a Bahtinov mask, now with the Barlow lens in place. 10. Slew to the target planet. 11. Roughly adjust the mount to bring the planet in the camera field of view using the finder scope as a guide. Then use the camera's snapshot preview mode and more precisely center the planet on the ASIAIR imaging screen crosshairs. 12. Switch to video mode, 1080p, and again precisely center the planet in the field of view on the ASIAIR imaging screen crosshairs. 13. Switch to 240p or the fastest frame rate setting. 14. Execute AVI video capture. Collect 60 to 90 second continuous video images of Jupiter. That is the workflow that I determined from my experience. And from my perspective, it is the most efficient process to image any of the planets with a refractor telescope and a Barlow lens. Also, as you may have surmised, once you have completed imaging your first planetary target, it is straightforward to slew to any other planet or the moon and continue with further imaging. As long as the finder scope is calibrated precisely with the OTA you just configured. All you need to do is slew with the ASIAIR and use the finder scope to zero in. The process is surprisingly fast and easy for imaging those additional secondary targets. In the next video, I will explore more about the proper exposure times and gain settings and what filters are best for capturing images of Jupiter. I'll have lots of raw video images and photos of Jupiter to show you, so I hope you will join me again in the coming episode. Here in Yokohama, I am JPAstroGuy. My name is Paul Cheesegel, and you have been watching Astrophotography Japan.